Swayam Prabha. Digital India. Educated India.
So, in this lecture I am going to discuss with you about solidification behavior of some of the ternary alloys in which a ternary eutectic reaction is present. But before that we will do some recap of the previous things. So, we have been discussing of ternary system in which there is a ternary eutectic reaction, and the eutectic reaction is like this: liquid going to alpha plus beta plus gamma, liquid transforming into 3 solid phases simultaneously, alpha plus beta plus gamma. And for that to have, we need to have binaries in which eutectic is present in all the binaries, like between A and B, B and C, C and A, you have eutectics, correct. And if that is the case, then ternary eutectic will be present. For very simple reason, I have removed in this lecture the terminal solution regions. I have done that in the last lecture, but then I thought that will complicate the phase diagrams and also analysis. So, that is why I am showing you very simple picture of a ternary eutectic where all the binaries from eutectic, but none of the binaries terminal solution region exist. So, that is what is this ternary system. A, B, A, C, B, C, all of them have ternary eutectics present, binary eutectic present, sorry. You can see here there is a eutectic present in all the cases, and because of that, as I told you in the beginning, because of that there will be a ternary eutectic present, and which will lie inside the Gibbs triangle. Obviously, that is why it is called ternary eutectic, and it is a true ternary eutectic. Why? Because not only the composition lies inside the ternary Gibbs triangle, but also the eutectic reaction involves 4 phase equilibrium. That is why. This is obviously different in contrast to the ternary eutectic, in which is extension of the binary eutectic, which we have discussed in the case of 3 phase equilibrium, correct. So, that is not a 2 ternary eutectic, but here it is a 2 ternary eutectic. And the phase diagram will look like this. I have shown you earlier also. You see, these are the binary eutectic points 1, 2, 3, and the ternary eutectic points is there. It lies well below the 3 eutectic points in the binaries, correct. And the liquidous surfaces will look like this. It is shown here. They are actually like going down, forming a valley in the 3 binary eutectic regions, and one can actually draw these liquidous surface projections on the Gibbs triangle. They look like this. You can see this is a binary eutectic, this is a binary eutectic, this is a binary eutectic, and ternary one is sitting inside the Gibbs triangle. And one can also draw actually temperature contours as is shown on the ternary phase diagram. This is the temperature contours, and because there is no terminal solution, so therefore these regions will be A plus liquid, B plus liquid, C plus liquid. It is in contrast to alpha plus liquid, beta plus liquid, and gamma plus liquid. This is much more simpler for you to understand and grasp. Okay. So, obviously, now once I know this plot, this projection, it is very easy for me to understand solidification behavior, which we will discuss in a moment now. And now one can actually use color plots, which is easy. That is the reason I actually use PowerPoint projections. And as you see here, these are the contours, color contours, and it is going down just like a tea garden. If you have visited any hill region, tea gardens will look like this. The tea gardens going down, and all the tea gardens from the 3 coordinates of the Gibbs triangle are going down and meeting at a point E, and E will be a invariant point, because 4 phase equilibria will have invariant, it is invariant in nature in ternary system, because f is equal to 0 when number of phases is equal to 4. So, on the projection side, if I project the whole thing, it will look like this. This is a ternary eutectic and these are 3 binary eutectics, and they are just extension of these binary eutectics, these binaries ones, it is obvious, but ternary one is not, it is a 2 ternary eutectic. Space model, I have been showing you many times. Space model will look like this, liquid surface, as you have shown, it is much clear here. This is a liquid surface going down and meeting at this point. Okay, and these are the regions of y plus, basically I have changed from ABC to XY, let us do that. So, this is B plus L, this is B plus C, C plus L, this is B plus L, A plus B, A plus L, right, that is all. This is A plus L, C plus L, B plus L, and this is a eutectic point. Well, now I show you the real space model in terms of the picture. Okay, you see here what is actually happening. If I look at carefully, there are 3 eutectics E1, E2 and E3 present on the binary side. This is the binary, this is the binary, this is the binary. You can yourself draw, I am going to draw it on the board itself to show you. Now, what happens actually, the ternary eutectic point is sitting on this triangle ABC. Okay. This is sitting on the ABC triangle. Obviously, this 4 phase equilibria is what? It is consisting of 3 phase equilibria, not 3, 4. It is basically alpha, liquid plus B plus C, liquid plus A plus C, liquid plus A plus B, 3 phase equilibria, and each one is a triangle, right. As we have discussed in the previous lectures, 3 phase equilibria will form a triangle, right. That is obvious, because that is how we have discussed the 3 phase equilibria. So, when the 3 triangles meet, they form the 4 phase equilibria point, and that is the point because it is invariant point. And in between you have C plus L, this is A plus L, this is B plus L, this is also B plus L. These are the regions of solid plus liquid. Okay. So, now if you project the whole thing on the triangle, much easier. This is just projected here, E2 is here, E2 is here between A and B, E3 is here between B and C, and E1 is here between A and C, right. And these lines, this one E3E is this one, you can see here E3E, E1E is this one, and E2E is this one, they are just projected simply from 3 dimensional to 2 dimensional projections, correct. Now, what will happen? Now, these are the temperature contours, okay. T3, T4, T5, T6, it goes from T1 to T6, temperature is plotted. Basically, this is the way temperature are going down. See, if I take alloy composition like this, it is very easy. What will happen for solidification? Okay. Let us carry forward and discuss. Okay, let me show you that there are many systems which form ternary eutectics. Aluminum, copper, silicon is one such. Then you have a system gallium, indium, tin. Okay. Bismuth, indium, tin. Then this one is aluminum, copper, silicon. These are the system which forms 2 ternary eutectics. How do you know this is a 2 ternary eutectic? Obviously, there will be 3 phases. You see here there are 3 phases here. Aluminum is white. I will tell you why also. Aluminum is black. Aluminum is black. Then silicon is needles. These are the needles of silicon, and this is Al2Cu. This one is Al2Cu. This is a basket image. So, therefore, the phases which has the highest atomic number will be shown as a brighter. Aluminum has the lowest atomic number out of these 3 phases. It is basically not aluminum, it is alpha aluminum, because it will contain copper and silicon both, but silicon will be pure, that is why silicon comes in needle. So, therefore, 3 phases coexist in the microstructure, that is why it is called a 2 ternary eutectic. So, now this is what we are going to spend a lot of time, how the solidification will happen. In this case, in this system where there is no terminal solution, obviously alloys, there are many alloys which will undergo ternary eutectic reactions, not only the alloy which has exactly ternary eutectic composition corresponds to E, but a corresponding composition corresponding to X, Y, even composition corresponding to X and Y, they will all actually, because they are falling on the what is called the regions of A plus E liquid or B plus liquid or C plus liquid, these are falling on the this cups of the liquids. Okay, these cups, any of these cups, on these cups, this one or this one or this one, they will be basically solidifying as a ternary eutectic. Not only that, alloys which actually forms which are actually forming, suppose this one U1 will also form the ternary eutectic. So, let us now discuss a general case. I take an alloy composition X prime denoted by this line, okay, X prime, you can see. So, what will happen as it cools down? Remember that binary, okay, let me just tell you the binary, okay, binary is easy, and I am just drawing the simplest possible binary phase diagram between A and B. And if I take an alloy composition X, what will happen? Nothing will happen. This is liquid, this is A plus B, this is B A plus L, this is B plus L, right. What will happen? If I cool it down, nothing will happen above this temperature. This is the temperature T1 or TL, nothing will happen, it will remain liquid. Only if you cool it down below the temperature TL, it will start forming A, pure A, obviously, because there is no terminal solution here. Remember, this is in opposition to this phase diagram. Correct. So, if I take an alloy like this, it will precipitate alpha, but here because there is no permanent solution region, there is a terminal solution region. So, therefore, this will precipitate A and B, whichever it is a hypo or hyper-eutectic alloys. So, as you have considered hypo, it will precipitate, keep on precipitating A, and as it precipitates A, the liquid will reach in B and B, more and 1 B as the temperature goes down. You can see here, this is the tie lines. So, finally, when the eutectic temperature will reach, whatever liquid will remain, this will form the binary eutectic between A and B. Exactly same thing will happen here, exactly same thing, but in a ternary space, model, it will be shown that way. So, if I take alloy X, I pull it down, only when it touches the liquidous surface at point 3, this will precipitate C, remember, this will precipitate C, correct. So, that is what happens at T3, at temperature T3. Please have a look carefully. At temperature T3, the alloy composition line hits the liquidous surface. As it hits, obviously below that temperature, C will precipitate, start precipitating. What will happen if C starts precipitating? Liquid will be reach A and B. So, that is why the liquid composition will follow along this curve, okay, this curve. Got it. So, what will happen? Liquid composition is following 3 to 4 prime to 5 prime to 6 prime. 6 prime something else happens. What is that? 6 prime is a point which is lying on the line or intersection line between E1 and capital E. E1 is the binary eutectic between A and C, and E is the ternary eutectic point inside the Gibbs triangle. So, what will happen? Because it is lying on this valley between E1 and E, small e1 and E. Okay. So, still the temperature T6, this is going to precipitate only C, but as it touches, as it reach the temperature below T6, that means what? As it touches this line, this valley E1 and capital E, this will also start precipitating A. Why? Because this is the cups, or this is the valley which is sitting on A and C. Am I clear? So, try to be very clear. Do not look at the bottom. Just try to see what is happening on the space model in the 3-dimensional picture. So, as I cool it down, only at temperature T3, some crystallization will happen, and this crystallization will be of C. So, and as the temperature is going down from T3 to T4 to T5, more and more C will crystallize. And as when the temperature reaches T6, this liquidous curve or liquidous surface is going to meet the valley small e1 to capital E, okay, this valley, and once it touches that, this will precipitate A also, okay, this will precipitate A. Now, further on, as the temperature is going down, the liquidous composition will follow 6 prime to 7 prime, precipitating more amount of A, and finally it will arrive at E, where all the 3 A plus B plus 3 eutectic will crystallize out. That is what is going to happen. Now, one has to carefully look at it, carefully look at the Ternary space diagram. This is exactly the same way as I have discussed the binary one. In binary, first it crystallizes primary A, then the liquid composition becomes rich in B as the temperature goes down, and when the liquid temperature reaches eutectic isotherm, it undergoes eutectic reaction between A and B. Okay, liquid transform A and B. But in ternary, you have 3 phases, A plus B plus C here in this case. So, therefore, before that ternary eutectic reaction happens, crystallization of both C and A should happen. But remember, as eutectic composition is more rich in B. So, therefore, in order to reach the eutectic composition, in order for the liquid to reach the eutectic composition, A and B should get out from the liquid as a primary solid or primary dendritic phase, as you may call, and then it will reach point D and form the eutectic. That is very easy. Now, you do not need to do all this stuff. Let me see what I have. Okay, you do not need to do all this stuff. This is little bit cumbersome, because one has to draw the 3-dimensional diagram and discuss this. If you have a projection of these surfaces, all these surfaces, liquid surfaces onto the Gibbs triangle, then even things are much easy. Let us see what happens. I have the projection of these. Now, I concentrate only on the bottom Gibbs triangle A, B, C, and these are my projection E2 to capital E, E1 to capital E, E3 to capital E. These are my liquid surfaces projections, correct, and my alloy composition lies on this point. Now, what is this phase field? E1E, E3C, this is phase field of primary C plus liquid, obviously. Similarly, this is a phase field E2, E and E3, this is a phase, or B, this is a phase field of primary B plus liquid, and this one A, E2, E, capital E and E1 is a primary phase field of A plus liquid. So, as the composition lies on the primary phase field of C plus liquid, the first crystallization product will be C. So, how do you do that? Very simple. I join this point x prime with C and extend this line on this side. So, what will happen? If I extend this on line, it will keep on going like this, 3 prime, 5 prime, 5 prime, it is 6 prime. 6 prime, it is hitting the liquid surface of, or the valley of E1, small e1 E. Remember, this is the connection of binary eutectic E1 with the ternary eutectic capital E. So, therefore, if the alloy composition, liquid composition sitting on this curve, it must precipitate A and C both, because that is basically binary eutectic reaction. It will crystallize both A and C. So, till one point before 6 prime, or temperature little bit above 6 T6, this will crystallize C only. Once it reaches 6 prime or temperature T6, this has to crystallize both C and A, because the point is lying on the surface of E1E, and that is basically connects the binary eutectic between AC and the ternary eutectic point. Now, onwards is very easy. This is going to follow 6 prime to 7 prime to E, and E is the lowest melting temperature point in the phase diagram. So, everything will solidify at point capital E. So, now I go back here. Now, you see it is very easy. Suppose this is my alloy the composition, and I want to know what will happen to solidification of this alloy. What I will do? First thing I will do, let me follow me, I connect this point with B here, because this is the primary phase field of B. B is basically coexisting with the liquid. So, as the temperature goes down, this will mass precipitate B, not anything else. Now, I extend this line, just I draw a line, basically you take a slide ruler and just draw a line between B and this point and extend it to that. So, as you see here, from this point onwards, temperature is going down T3, T4, T5, T6. So, till T6 it is going to precipitate B, right, it is going to precipitate B only. Now, at this temperature, this is sitting on the curve of E2 E, capital E, and E2 is what? E2 is eutectic between A and B. So, therefore, if it is sitting on it, it must crystallize both A and B together, and then onwards it will follow this way, and it will where the ternary eutectic reaction will happen. Is it clear? That is very easy to understand. Similarly, if I have a alloy composition like this, I can draw a line between these two, and join and goes. That is very easy, right? Not very difficult. Now, upon giving you this concept clearly understandable way, I would just like to you touch upon a little bit on the complex diagram. That is what I have to draw it on the board and show you how things possible. Let me try. It is not an easy diagram to do, but I will try. Okay, otherwise I will show you on the slides the next lecture. Okay. So, there are 3 binaries. I think I have 3 colored chalks, but remember I am going to draw the primary phase field of A, B and C, and this is going to be a little bit complex. That is why it will look like here. So, this is my C, this is my B and C. Okay. So, this has to be drawn in an angular way, otherwise you will not realize it. I have a red color chalk, yeah, and this one okay. So, these are the 3 eutectic points between A and B. Let us say this is E1, between B and C E2, and this is B and C E3, and if I connect these 3, I get into ternary eutectic point E, right. So, it will sit on a triangle. So, let us do that. This is one point of the triangle, and then okay. Correct. So, E is sitting inside the triangle A, B, C, and we can also draw this one. We draw by white chalk. It is better to draw by dotted line. That is how our ternary space model will look like. Now, if I want to know solidification of an alloy, that is what I told you, it is going to be a little bit cumbersome like this. How it is going to happen? Okay. Just I would like to tell you that I am teaching from this book of Alan Prince, where figure number 181 is nicely shown things. So, obviously, as it goes down, it is going to touch the liquid surface here, and from then this is going to follow this route, and solidification will be over like this, correct. What does it mean? This is the track of solidification pathways. What does it mean? This means that as the alloy composition goes down this way, it will start precipitating alpha. Remember, this is alpha, right, alpha phase field. Solution between A and C is, or A and B both, this is alpha phase field. If you connected these two, this particular space field here is alpha. So, it is going to precipitate alpha here, and this is be the alpha, this is the way alpha, and alpha will have a composition of alpha 1, which you can obtain from that. Then this will follow, the solidification solid will follow this way, okay, and it will reach this point, sorry, this will reach point A, correct, and this is the solid composition variation, okay, how this way. But if you look at carefully, as this will first thing it will precipitate is alpha 1, and as it goes down, it is going down and slowly reaching the E3 and E3, sorry, it is reaching, no, it is reaching not E3 here, okay, here it is reaching E3 and E. So, E3 and E is the eutectic between A and C. So, therefore, as it reaches E3 and E curve or the valley, it is going to precipitate both A and C. So, alpha and gamma, this is gamma, alpha and gamma, it is going to precipitate, okay. And because of that, what is going to happen? Because of that, liquid will become rich and reach in B more, and finally it will reach the eutectic composition, and it will solidify as a full 3 phase alpha plus beta plus gamma. That is what is going to happen. So, same thing will happen in any of the other compounds sitting on this, suppose this side or this side or this side of this phase field. That is what you have to draw yourself and try to understand, okay. And this is the reason I have basically touched upon the basic thing of the eutectic, where there is no primary phase field A, alpha, beta or gamma, only pure A, pure B, pure C exist, okay. And whenever, another important thing I should tell you, that whenever this is precipitates both alpha and gamma, there will be 3 phase equilibrium between alpha, gamma and the liquid, and that will look like a triangle inside these. I am not drawing it, this will make the picture very complicated and you will not be able to appreciate that. So, it is not difficult for you to understand. Again, this is going to follow, liquid composition will follow like this, the way I have drawn in the case of shown in the case of A plus B plus C. So, in the next lecture I am going to take a snapshot of this scan and show you, and try to make you believe, make you understand that from the position of the liquid surfaces how it is possible to discuss the phase formation.